Greetings, everyone. My name is Louis Hill. I'm the HVAC Product Market Manager for Drives. Our topic for today, motor technologies and VFDs. Thanks for joining us today. So here's our agenda. We're going to talk about the different types of motors that are available and used in HVAC applications. We're going to discuss how these motors work, what's needed to run them, and what are the advantages and disadvantages of each type. Here's a slide on some high-level motor technologies terminology. So we'll reference as the IM as the induction motor, ECM or EC be electrically commutated. We'll talk about the SynRM, which is our synchronous reluctance motor. We'll talk about the FACER, which is a ferrite-assisted synchronous reluctance motor. The starting methods that would apply. In some cases, it would be direct online or across the line. In other cases, it would be VFD operated. We'll mention that in the slides. We'll talk about stators and rotors, I-squared-R losses, integrated motor drive or integrated drive motor applications. And then we'll get into these non-salient to salient pole motors and their rotor designs, just at a high level. The first motor technology we'll discuss is the AC induction motor. The AC induction motor is the iron workhorse for all industries. It consists of typical motor components like a rotor, we've got a frame, we've got a stator, and we have a shaft. So how does it work? So what we do is we apply an AC current to the stator windings. This produces a rotating magnetic field. This rotating magnetic field then cuts across the rotor bars and induces a current in the rotor. Then this rotor then creates its own magnetic field. And the interaction between these two magnetic fields is what produces the motor's torque. This motor is considered asynchronous because the speed is not perfectly synchronized with the rotating magnetic field or the AC power line frequency. The motor shaft always run at a speed slightly slower than the speed of the rotating magnetic field. This speed is called slip, and this slip is what's important for the development of torque. So here we have a slide that shows a typical 25 horsepower, 1770 RPM motor with a NEMA premium efficiency of 93.6%. Now for this motor, it is possible to start it across the line. When we start it across the line, the slip is at 100%, meaning that there's 100% speed difference between the speed of the frequency versus the speed of the shaft. And that's important because that's what causes us to develop that torque. As you can see, during the starting mode, we are going to draw about 625% of full load current on this motor. And that's pretty typical for other motors of its size. We can also see that it's going to produce a 135% of full load torque during this period of time to begin turning that rotor and that connected load. Once we get up to speed, the motor will have a normal operation and some slip of about 30 RPMs. And that's the normal running area here highlighted in the yellow section towards the end. So as it's accelerating, what you'll see is the motor will run between that speed of 1770 and just under 1800 RPM. So 1770 would be full load and close to 1800 would be no load. Another thing that can be applied to this motor is the opportunity of a VFD. Induction motors can operate on VFDs, and this is a common occurrence in most industries. With a drive, we can vary the ratio of the voltage and the frequency. This gives us the variability to operate at any speed and have enough torque to do that work. Some key benefits of using a VFD on an induction motor: well, there's no inrush, right? We're at 100% or 110% or 150% torque, depending on what your application is. So we reduce mechanical stress. The power factor on a drive improves it on your system utility. Usually power factors on a induction motor is a little less than if you would put it on a drive. And most importantly, energy savings. By operating the load at the required flow, this eliminates any needs for mechanical means of flow regulation. So let's shift a bit and talk about efficiencies and losses. As you can see in the chart on the left, the larger the size of the motor, the higher the efficiency. So as an example, this red line here is a 5 horsepower line, and the purple one up here is a 200 horsepower line. So you can see as we get a little bit higher horsepower, we have higher efficiencies. And this is accomplished by the higher level use of more active material in the motor. And when I say active material, I mean copper and magnetic steel. So every motor in this presentation will be looking at the premium efficiency motor level, and it excludes any drive connection on it. So we're just looking at the raw motor. So now I'll talk a little bit about the losses. On the right, we see the losses in the induction motor. The yellow is losses in general, and then the items in red is the rotor losses. So you can see that we've got a lot of losses that we can try to reduce. So some of the losses that we see: magnetic core losses, which would be seen in hysteresis or eddy currents. Windage and friction. We've got running the motor cooling fan gives us our windage, and bearing friction can also slow down some of our efficiencies. We've got these variable losses, which change with the load on the motor. So our stator, which generally is the largest loss in the induction motor, is losses due to I²R losses. That is resistance in the stator windings, which is generally rejected by means of heat. We also have rotor losses, which is basically the second largest area of losses. So again, these are our I²R losses due to resistance in the rotor bars and end rings. We have also stray magnetic losses. This is due to the magnetic fields in the motor spreading out, not being efficiently managed or used. And this leaves us wondering, well, how can we get away from these losses? As we walk through these different motor technologies, we'll see about how we can get rid of some of these losses. So some concerns for induction motors. Well, we have a high starting current when used on a direct online or across the line starting application. But this really isn't a problem if we use VFDs. Speed decreases with load. That's our slip. I²R losses. That's heat rejected from the copper being rejected as heat inside the housing of the motor. Here are some advantages. We've got a simple to use and rugged construction. It's been around for a long time. Relatively low cost as compared to other motor technologies. Low maintenance costs, and it doesn't really take a lot to maintain these. Keep them lubricated, keep them cool, and you're looking at a long life in operation. These induction motors can operate on direct across the line or VFDs, which is great flexibility. Generally, these motors can be installed in almost every environment. As you can see here, we've got a variety of different motors that we're showing here. We've got this stainless steel washdown, white washdown. We've got this gray explosion-proof motor, and we've got this severe duty motor back here with general purpose motors. So we've got a wide variety of motors that can fit most applications. Highly available. Baldor makes these motors all day long, every day, and highly available are these induction motors. And they can be serviced. We have motor shops that can service these. Some customers can even maintain their own motors, replace bearings if needed, or rewind motor windings if they short out. So as you can see, there are way more advantages of using an induction motor than there are concerns. So this technology has been around since the 1880s, and there's been considerable work done to improve performance and energy usage. The induction motor will continue to be the workhorse in all our industries for years to come. The next motor that we'll look at is the electrically commutated motor, or ECM. The ECM motor looks much like the AC induction motor in its design. It has stator windings, it has a rotor, and a means of mechanically fastening a load. First of all, with the ECM, the stator works the same as an induction motor. When a three-phase AC current is applied to the stator, it creates a rotating magnetic field. However, the rotor is a little different. The rotor consists of permanent magnets, which can be configured in a variety of ways. The drawing here just shows kind of a simplification. But the rotor poles then are attracted to the rotating magnetic field poles, and the motor rotates. The design keeps the magnetic fields synced, so the drive needs to be paired with the motor, and the rotor will spin at the speed of the rotating magnetic field. ECMs come in a wide range of sizes and package designs, and we'll see those in the next slide. The use of permanent magnets in the motor, specifically in a rotor, allows for this flexibility. In this presentation, we will be considering the 50 horsepower or less applications. It's important to define what an ECM is. So generally speaking, the integration of a PWM, pulse width modulated drive, into a fan motor drive package is generally considered as to be an ECM. But as you can see in these pictures, they come in different shapes and sizes. The two on the far left are what we would consider an ECM package, whereas the other two would be like an integrated drive motor or a loose drive, either connected locally or remote mounted. For the intent of this slide deck for the ECM, we'll couch our terms in the most popular ECM packages here on the left. So here we have a bar graph that shows the efficiency of each motor when it's running at full speed and at full load. As you can see, the premium efficient induction motor is a little less, 2 or 3 points less than the equivalent ECM motor. And this is primarily because of the use of permanent magnets, right? We've reduced quite a bit of rotor losses. The ECM has very good efficiency at light load. If we look at this graph over here, you can see that we're between about 93%, a little less than 94% efficiency at 25 to 30% load. And you can see that the 5 horsepower induction motor equivalent is much lower, just under 86%. We can see that it drops off quickly on the induction motor, right around 60%. While the ECM's efficiency is always the higher one, when we look at the graph, a couple things we should see is that the range drop of this graph only goes down to 86%. So we don't know what it looks like below that. And it might be insignificant at that point, right? So it's more often to use power demand than efficiency over the wide range of loads to see how this motor will perform. So what are some advantages of using ECM technology? Well, as we just saw, higher efficiency at partial loads. But those higher efficiencies might be insignificant. Low heat generation, again, they have less losses. Compact and lightweight, they're able to accomplish that because of the permanent magnets. Low acoustical noise. The motor inherently has a higher power factor. That's because of the electrical design. When the drive is built into the ECM, wiring the system is quite simple. You don't have to go between the drive and the motor. So due to these advantages, ECMs have gained popularity. Let's look at some concerns. The ECM receives its feedback from the motor as the magnets pass by the stator's coil. So the ECM must synchronize to the output of the position of the rotor, which requires a drive. Because you need to keep this synchronized, you cannot start ECMs directly across the line. It's not possible at this time to run multiple ECMs from a single drive. They all have to be synced up. So that's why we do a one-to-one. And the motor requires the use of strong magnets. So either powerful ceramic or rare earth magnets are commonly used. And as we've seen in the past, those rare earth magnets are very hard to maintain a good supply chain on those. So it's important to really understand some of the motor designs or the rotor designs. The rotor designs come in very, very different shapes. We have salient pole and non-salient pole. And salient means projecting, so it describes the magnets in the rotor being embedded in the rotor and pointing outwards. Some other ways of explaining what this salient pole permanent magnet is might be known as interior magnet motors or buried magnet motors. The ACS 880 can support both non-salient and salient pole motors, and the ACH 580 doesn't support salient pole motors, only non-salient pole. These motors can be difficult to service. Because they're so compact, it's almost impossible to pull them apart. If the motor is freewheeling, there is a safety concern. Even when no power is applied, its permanent magnets will generate voltage at the motor's terminals. You really need a skilled electrical person to know how to maintain this type of equipment. When dealing with packages that include ECMs with the integrated drive, it's often hard to service this drive and this motor separately. Some manufacturers say just return it for service or an exchange. There's usually no local control panel. All the work needs to be done through either some kind of serial connection or other control network connection. Such a small drive in itself can hardly provide any harmonic mitigation. You might have to look at harmonic mitigation for the whole system, your electrical system, which could get large and expensive. As you can see, there's many concerns about using ECMs in your applications that you need to think about. Now let's talk about the Synchronous Reluctance Motor, or SynRM. The simplified drawing here shows a modern SynRM motor. The SynRM uses the same stator as an AC induction motor and uses a special rotor that's made of thin magnetic steel sheet laminations. Once the AC current is applied to the stator, it produces a rotating magnetic field just like the induction motor. Because of the special rotor design, it creates a magnetic field when induced by the stator. And the way it does this is by allowing the greatest magnetism to flow across the steel path and follow the rotating magnetic field. The white air gaps or flux barriers don't allow an easy path for magnetism to flow. This reduces stray magnetism. As a result, the interaction of the two magnetic fields produce the motor torque, and the stator and rotor magnetic fields are synchronized and rotate at the same speed. A good analogy of how it works would be like a compass. In this picture, the above and the rotor acts as a 4-pole needle compass. So now let's look at efficiencies. The SynRM doesn't operate by inducing current into the rotor. As a result, it avoids the I2R losses and the heat generation that the induction motor has. You can see here that the SynRM motor efficiency is just slightly less than the ECM, but improved over the premium efficient induction motor. The part load efficiency of a SynRM follows the same curve shape as the asynchronous AC induction motor, but at a higher level. The power factor of the SynRM is also lower than that of an ECM. It draws more current. This results in an increase in the I²R losses in the motor's stator, which cause a slight reduction in the motor's efficiency. Concerns about synchronous reluctance motors. It needs to be controlled by a VFD, so it can't synchronize itself from a dead stop. It is essential to ensure that the VFD is designed to work with the SynRM. The power factor of a SynRM tends to be quite low, so when selecting a drive, make sure it has not only SynRM capable software, but that is also sized for power and current. Advantages. Well, because there's no current is passed through the rotor, the core of the motor stays cool, and this can help extend the life of the bearings. A cooler SynRM rotor means significantly lower bearing temperatures. And this is an important factor because 70% of all planned motor outages is due to bearing failures. The stator windings are the same as those used in induction motors. And because we don't use permanent magnets in this motor design, the rotor uses the stamped laminations. The cost is less. And it's easier to service. You can repair this motor and rewind it and replace bearings. Just contact your local motor shop. The final motor technology we'll look at is the ferrite-assisted synchronous reluctance motor, or FACER motor. The FACER motor is the future for 50 horsepower or less motor designs. Here we have the ABB Baldor Alliance motor called the EC Titanium. It is a true FACER motor. This one pictured has an integrated VFD, but it's also available without a VFD. Here we have the motor frame. We've got a rotor, we've got a shaft, we have a cooling fan, and the rotor has ferrite magnets embedded in the rotor, and that's what we're going to talk about this design. So in reality, the FACER motor operates much like the induction motor and SynRM designs. The AC current in the stator windings produces the rotating magnetic field, just like in the induction motor and SynRM motor. The special rotor design uses ferrite magnets that create the magnetic field when induced by the stator. Three things that these ferrite magnets do is they improve the power factor, they help boost the efficiency, and they produce more torque by increasing the magnetic field in the rotor. And because of this interaction of the two magnetic fields, it produces the motor's torque. And torque is produced in two ways. The first is created by the design of the rotor, and the other by the interaction of the magnets in the rotating magnetic field. The stator and the rotor magnetic fields are synchronized and rotate at the same speed. So again, it works much like the needle of a compass. So let's look at efficiencies. And I want to highlight some efficiencies here just so that we get a gauge. So IE3 would be our standard NEMA premium. IE4 would be a step above that called NEMA super premium. And then finally we have this IE5 ultra super premium. And these lines are shown here for you to look at. But the global benchmark is IE5. And that's shown by this yellow dotted line on this graph. And as you can see, the black with the square lines is the ultra super premium NEMA efficiency. And you can see that we meet or exceed it along this line. The colored lines, the red, blue, and purple, those are the NEMA frames that are built with the EC Titanium ferrite-assisted synchronous reluctance motors. And as you can see here, there's a couple of them that overlap. This red and this blue overlapped. What this tells us is it gives us an idea that shows that we have some power density here that we can take advantage of. So we can put a smaller motor to do a higher framed motor work. And that's important, and we'll call that out in a little bit. But as you can see here, here's our induction motor efficiencies. Here's the IE4 super premium efficiencies. And here's the IE5. So as you can see, the EC titanium meets or exceeds the global IE5 standard. So now let's look at this efficiency and fan speed, fan load and speed chart. So here we've got our load, and this is our quadratic load. Here we have our EC titanium motor at the highest efficiencies. Here we have an ECM motor, and then here we have our induction motor. So you can see that we have superior performance above the ECM at both rated and part load speed points. So it's important to note the gap between the efficiencies. We have in the EC titanium, or the phaser motor, a wider speed and torque range that allows more flexibility. So now we can match up a fan impeller to reach the most nominal fan duty point. And potentially we can overdrive the EC titanium beyond base speed because we are just only limited by output voltage. So really there's only one concern that we have with the ferrite-assisted synchronous reluctance motor, is that it requires a drive. It's not able to run direct across the line. But let's talk about some of the advantages. One of the advantages is a higher total system efficiency at full and part load conditions. We're going to minimize the environmental impact. We're not using rare earth magnets, we're using ferrite magnets. We have extreme low starting current and less cogging, so this reduces mechanical stresses and produces a very quiet operation. And we saw a little bit on the power density of the higher ratings per the frame size. So we can put a smaller motor in a traditional footprint that reduces cost and saves valuable space. So as you can see, the advantages far outweigh the disadvantages. So now let's just do a final review of the motor technologies that we talked about. So this list will provide a summary of each type of motor. So with AC induction motors, the efficiencies continue to improve, although energy loss in the rotor bar is a concern. They can run across the line or on a VFD. Electrically commutated motors, or ECMs, these rotors use permanent magnets to improve their efficiencies. Could be a problem if rare earth magnets become harder to come by. They require a VFD that's designed for the type of ECM they are. And it may be hard or impossible to service the type of ECM that you have. Synchronous reluctance motor, or SynRM motors, have a special rotor and a standard stator, and this provides near ECM efficiency. However, it does require a VFD that's designed to control SynRM motors. Another advantage is that it's serviceable. It's much like the induction motor can be serviced by your local motor shop. And finally, the ferrite-assisted synchronous reluctance motor has the same features as the synchronous reluctance motor, but it has a higher part load efficiency over the ECM. We have marked improved power factor and torque over the SynRM, and increased power density and saves space and cost over the induction motor. That concludes this presentation. Thank you for your time.